This is the last of our momentum videos, and we are going to talk about impulse, which is represented by a J. I don't know why it's a J, but it is what it is, a J. And how we're going to look at impulse is we're going to look at two objects that are going to run into each other, one of them with a velocity and the other without a velocity, and they are going to collide and stick together. And by using the velocity of center of mass, we can find that we have mv over 2m, and the m's cancel. Let me try that again. And we get v over 2. So our velocity of the objects after they stick together is v over 2. Now we can see that for the system, here where we had a completely inelastic collision, for the system, that momentum is conserved. And we need that to happen. That's important for what we're doing moving forward. So if we look at each of the masses individually as mass 1 and mass 2, for mass 1 we have an initial momentum that was mv, and final momentum that was mv over 2, and then it had a change in momentum that was negative, that was mv over 2. Then if we look at mass 2, its initial momentum was 0, it wasn't moving. Its final momentum was mv over 2, so its change in momentum was positive mv over 2. What we can see in this collision is that the first mass loses some momentum, and the second mass gains the momentum that was lost, showing that momentum is conserved. Whatever mass 1 lost, mass 2 gained. And therefore, for the system, momentum was conserved. Now, something had to cause this momentum to change. Something caused this loss and this gain. And when Newton started looking at this, this is how he came up with his third law. And so impulse, studying the last part of momentum leads very nicely into forces. And so this is where Newton came up with his third law, that there had to be something that caused this change in momentum that was equal and opposite. So forces act on the objects equal but opposite in direction, and they also act on the objects differently. They act on two different objects. So forces occur in pairs but opposite pairs, and the forces occur on two different objects. We'll cover that a little bit more when we get into forces. But you can see that there was a force that acted on mass 1, and the exact same force acts on object 2, mass 2. So now let's talk in general about change in momentum of an object. So if we have change in momentum of any single object that happens to have a collision where momentum is conserved, the change in momentum for that object is the mass of that object times its change in velocity. If we were to treat that as a function of time, we would divide it by time, and then we would have the change in momentum as a function of time, or divided by time, is equal to the change in mass times the change in velocity of time. And we know that the change in velocity over time is acceleration. The change in velocity over time is acceleration. So the change in momentum as a function of time equals the mass of that object times its acceleration. And we know that ma equals force. So now what we have is that force equals the change in momentum of an object, of that single object in that collision, as a function of time, or mass times the change in velocity of that object as a function of time, or that it equals the mass times the acceleration. And this leads us into Newton's second law. That forces change the motion of objects. That's Newton's second law. It came from studying the change in momentum of a single object in a collision where the momentum was conserved, and the forces change the motion of objects. Now, if we were to solve for the change in momentum in the equation above, we would have force times the change in time by multiplying both sides by time. It's going to equal the change in momentum, which is also impulse. So what we have here is that impulse equals the force times the change in time, and it also equals the change in momentum of any object. Now let's look at something we've already kind of started in class, and we had a nice little discussion about it, but we'll go ahead and cover it now, is that we have a graph of force in newtons and time in seconds of a collision, and that collision peaks at a point where it was at its maximum point. So the force of the collision hits a maximum point, and then it leads into that maximum point and then goes away from that maximum point. So the force acted over some time. If we were to find the area under that curve, that area under the curve would equal impulse or the change in momentum. And this change in momentum is for both objects, or we could look at them individually. So it's a change in momentum for one object and change in momentum for another object. So the change in momentum for each object, one is going to be negative and the other is going to be positive. And we figured this out in class together, which is nice. But basically, if we look at what happened at the beginning example in class, or beginning example I had on this page, mass 1 lost momentum. So it's a negative momentum, and mass 2 gained momentum. And so therefore it's a positive momentum. And so we can look at it for individual objects. So in the end, this will make solving some of these problems easier. One thing I want to mention, I don't know why we talk about impulse and change in momentum as if they're different. They are exactly the same thing. The impulse is J, and change in momentum, change in P, they're the exact same thing, but in physics we talk about them as if they're different and then set them equal to each other. And I don't particularly know why, other than the fact that that's just how they do it. So we'll do some more examples of this in class, and get ready.